All right, hello everyone. This is Alec Powell, and welcome to the MemSQL 201 Advanced Tips and Tricks webcast. Today, I'm accompanied by my colleague Jeremy, who's on the line, who's part of the engineering team. Jeremy, would you like to go ahead and introduce yourself as well?
Hi everyone. Yeah, this is Jeremy with MemSQL, and I work with Alec. But I'm a relatively recent addition to his team. I worked on some other teams with some of our customers more closely over the past couple of years. So I'm going to be watching his presentation with great eagerness, and try to ask a couple questions as we go along too. This will be a learning experience for me as well.
Great. Thanks, Jeremy. And just to fully introduce myself to everyone, some of you may have spoken with me before. My name is Alec Powell. I've been working at MemSQL for 2 years in a solutions engineer capacity. And the purpose of today's webinar and future webcasts with us is going to be to talk about more advanced tips in MemSQL and capabilities of the product that our customers going a little bit deeper than just our documentation, and talking about the different use cases and ways that MemSQL can enable your business. And so with that, just to get a sense of the attendees on the line, we have a quick poll that we'd like to start, just so that I can gauge the interest level and experience level with MemSQL, the product. So for those in the audience, we have a quick poll that just started, and if you could choose the selection of how long you've been using MemSQL, that really helps cater our audience here. So the choices are anywhere from 0 to 6 months to 2 years and above. And so I will wait for the responses here. Thank you everyone for responding. Great, so it looks like about 43% are new to MemSQL with 0 to 6 months experience. We have 29% of users who've been using MemSQL for 6 months to a year, and 29% have been using it for 1 to 2 years. Awesome, and appreciate the feedback, everyone on the line. So what are we going to cover today? If I can go to my screen share. This is the agenda for today's webinar. So in this hour-long session, we're going to cover starting at the basic topics of MemSQL and then getting more fine-grained into things like query tuning and memory management in MemSQL. And so the goal is to solidify your understanding of the product as it exists today, and then walk through and specific new features that have come out that would help your operational deployments. And so while we go through this, there's going to be a few breaks for questions. And what we'll do is save some time at the end to go through any more questions in detail. So I believe there's a question asking tab in the webinar. So feel free to type and post a question, and then we can answer it at the end in the Q&A session. Great, so here's where we'll start. MemSQL, the row store versus the column store, and making the most of our 2 storage models. So as everyone very well knows, MemSQL as a product has both a row store and a column store format for your tables, as well as the ability to stream and ingest using real-time pipelines. MemSQL was originally built using this row store model where all transactions and data was stored in memory, and this accounts for most transactional or real-time use cases. MemSQL also now has a data warehouse capability with our column store, which came out several years ago and is now a robust part of the offering which has scalable analytics for your OLAP aggregation use cases. And so it's worth noting and differentiating the two based on the use cases that we talk about that MemSQL can be used for, as well as in practice how they're used. And so at a standard level, the row store table and column store table. The row store table, all of your data will sit in RAM and live in memory. In the column store tables, your data will live on disk, but it will be powered by memory. We use certain caching at the Linux level to look at some of your segments that are most frequently accessed. And we also leverage metadata about each of those segments. And so that's something that I'll get into more detail about. It's worth noting that both table types are persistent. So we do store everything in the row store in memory, but it persists to your disks for durability purposes using our transaction logs and our snapshots. And so this functionality allows MemSQL to respect ACID constraints and obviously protect your data. And of course, in the column store, everything is already stored on disk, and you have the ability to replicate both the row store and column store with our high availability feature, which comes with most enterprise deployments. So I want to spend the next few minutes going over and making sure we're aware of the different use cases in which row store and column store are best suited in MemSQL. So as we see it, use cases for the in-memory row store are more of an operational or transactional in nature, and they involve single records, whether it's inserting single records, updating single records, looking for single records, and any type of delete is also going to be very fast. The row store is backed by our skip list indexes, which are created as a primary key on each table. And so it's very easy to ingest data and also update data based on using those indexes. And because the rows themselves are kept in memory for you to actually access very easily. Once we start talking about the column store, this is where it's better leveraged for analytical workloads. So the typical queries and types of workloads that we see used in the column store are going to be more of a table scan, large aggregations, group bys, queries that look across large amounts of data, and rather than looking at single records. So it's worth noting the kind of best use cases for these two storage models. And it's also worth noting at the bottom that, again, in MemSQL, in practice, these are just table types. And so you can create tables in each storage model, and you can join these tables together if you wanted to. You could union the result sets together. You can interact with them the same way through your client or your application.
Hey, Alec?
Sure.
Hey, Alec, this is Jeremy. Sorry to interrupt, but wanted to ask a quick question about sort of the row store, column store sort of decision to be made here. So this slide, I think, does a great job of detailing kind of the sweet spot for row store versus column store. Row store for transactional, random seek performance, frequent updates, et cetera, and column store for more analytical workloads. Something I've seen at some of our customers is use cases that don't quite so obviously fit into like just one of these or the other. So do you have any sort of commentary on that about how to determine for use case X, which seems to have some transactional parts and some analytic parts? Sort of what's the decision process or the sort of the algorithm, if you will, for thinking about this?
Right. Thanks, Jeremy. And the answer to your question is obviously this is workload dependent, and so the most common practice that I would recommend is in working with our team as well is what we do is we try and scope test workloads, and in those cases we can look at the performance of both row store and column store using based on the queries or a test set of queries against each model and seeing how they perform. What also is effective at a lot of our customers is the notion of an active or hot data set as opposed to a cold data set. And so speaking towards the last point at the bottom of the slide, a lot of our customers, they will in fact keep the same schema in both a row store table and a column store table. And what happens is they have the most recently accessed data in a row store table, and the historical data or archived data. This can be used to serve queries using a view that would join or union the tables together in a fashion that looks like it's going to be coming from one table. It's also worth noting that for performance in the column store, there is a row store backed segment. So to help with the ingestion to column store, MemSQL has a hidden buffer row store table inside the column store. And this also allows customers to get effective performance from in-memory based on their most frequently accessed data. So as we said, the most frequently accessed data in your column store will be cached in memory as well to help your performance. And so those are the common ways, and obviously there's no cut and dry way of depicting your use case. So we have a lot of resources on our team at MemSQL, and in the future programs like our training and our office hours that will help our customers and users decide between these two storage models where it makes sense. So this is meant to be a kind of a guide to get those of us thinking about our use cases in the right way.
Okay, cool, thank you.
Great. So now we're going to move to the example that I'm going to be covering in this webinar, which is a simple star schema. And the way we have it set up is a randomly generated data set that looks at the healthcare industry, looking at drug orders and transaction history. So this use case is a simple star schema where there's one fact table that has all of our order history, and there are 4 dimensions. And so we've set up a MemSQL cluster to accommodate these tables, and we're going to test one query in particular throughout this exercise. So quickly, I'm going to go over to my MemSQL cluster here, and you can see the 5 tables on my screen. If we do a show create table fact supply order, we can see the different fields that are part of our fact table. And so this fact table is created as a column store table, which we're about to talk about how we do that. But the main columns in this table are the product ID, time ID, supplier ID, and employee ID, which all link to the dimension tables that we see in the schema. So this is the example that we're going to walk through throughout the rest of the webinar, and hopefully it's a good depiction of the use case that MemSQL can be used in, and obviously there are many more, but this is a simple one that we will work with today in this session. And now looking at our query, this is the query that we're going to be looking at, which is a simple query across all the tables that's going to join across all our dimensions, and looking for the attributes of the providers that have sold a product in the aspirin category that come from the city of Topeka. So this is, again, a randomly generated example. It's something that we might be running in our analysis of the transaction history based on our use case. So this is what we're going to try and accomplish. So quickly, I want to go over the column store delineation in MemSQL. So if we look at the schema again of our table here, we have the using clustered column store syntax. And so creating a table in MemSQL is very simple, and creating a column store table is is done with the addition of this special index or key. And so we'll see that right now it's based on time ID, product ID, and supplier ID. And what the index does for the column store is sorts each of the segments on disk in this fashion. So if we did not have this line of clustered column store, this table would be created in memory. And in our use case, because there are so many rows that are in this fact table, are going to be in this fact table, we don't want to create this in memory to overload the table capacity. So to put this in column store, we add this special index, and we sort it first by time ID. The sort order is necessary in column store because it helps us delineate how we're going to sort the data on disk in this columnar format. So to give another quick example, on a table that's similarly configured, and this is in our documentation, the ordering is first happening by price. So you'll see that the columns are all kept separately, but the price is organized and ordered such that the lowest items with the lowest cost are listed first. And after that, we subsequently are going to sort based on the product ID and then color. So the main benefits of doing this in a column store table are the effects of segment elimination. So segment elimination is a practice in our query engine that allows you to skip hits to disk during the query. And so if you're querying across a large data set, and in our case, it's going to be using the year 2016, it might make sense to sort based on a time attribute, because what we'll do is we'll store the minimum and maximum values per segment in memory in the metadata we keep for each table. And so this box here represents one segment of a column store table. The price is between 4 and 15. So if our query came in and looked for any product that was a price greater than 15, we would know that this segment can be skipped effectively because all of the rows in here are not going to pertain to the results of the query. So this allows our queries to get better performance in column store. It's a good tactic to take advantage of when creating a column store table. And again, this is what differentiates the column store tables from the row store tables. So if you want to store anything on disk, we have to think about the order in which we're going to be sorting on. And this will be our column store key that you have to add at the bottom of the schema here. So that defines the column store versus the row store. So that brings us to the next piece. How are we going to ingest data? Now, MemSQL has a product called MemSQL Pipelines, which was released as part of MemSQL 5.5 about a year ago. And this accommodates real-time data loading and ingestion. What's directly into the row store or the column store tables. And this happens because, as we talked about earlier, the column store has a hidden buffer table that uses memory and effectively uses the row store to process the data when it comes in. So most use cases where we see streaming happening to the column store are when you have a lot of data coming in that needs to go to a fact table, and it might be a one-time load or a load that doesn't involve updates of data or re-input. So you can stream it directly to the disks. The way that Pipelines is designed is to take advantage of the partition parallelism within the distributed system. And so this is something that we'll talk about in the next section, where I go over the sharding mechanisms and distributed system of MemSQL. And what happens is Pipelines, the product, allows you to pull in batches to each of the leaf nodes directly. And so any other form of ingest into MemSQL, you first have to go through an aggregator node, which may bottleneck you in terms of the network resources or just the throughput you're able to get from one machine. In contrast, the pipelines product places an extractor program on the leaf nodes directly, which then can pull a batch in parallel across all of your partitions within your leaf nodes, connecting directly to the data source itself. Once that batch is complete, in that fashion, and then it will continue the rest of the batches as part of the pipeline. So the idea with pipelines is that you can load in batches as if you were, loading from, say, an S3 bucket, which I'm about to show you. But you can also stream from places like Kafka, which are a real-time message queue or broker that will continuously stream data into the product and allow you to take advantage of this real-time analytics functionality that we provide. So now how are we going to load our table? This set of commands is going to show us how we load using an S3 pipeline. So I'm going to go back over to my MemSQL cluster and take this pipeline command.
Hey, Alec, I don't know if this is just me or other people as well, but the audio cut out for about 10 seconds in there. So
okay.
Do you mind just sort of briefly recapping with you, just in case other people also missed it?
Sure, on this slide here?
Yes.
Okay, so the idea, again, for those who might not have heard the whole thing, is that pipelines gives you a parallelism per leaf in MemSQL. And so in normal loading cases, you might be bottlenecked by the aggregator node for ingest because all inserts have to go through the MemSQL client. In pipelines, what happens is the MemSQL program or extractor makes a one-to-one connection with the data source itself, whether it's Kafka or S3, and pulls in back. And so this allows us to get the highest throughput and the best performance during your data loading processing. So what I'm going to show now is a test S3 pipeline. So I've copied the syntax for my orders pipeline. It's going to populate our facts table using my AWS credentials, and we'll see it connecting to an S3 bucket. So that pipeline was created. In fact, if I go over to our MemSQL cluster and then visualize quickly the files, once I get my mouse back. We can see we have a list of files here that are CSV format in my S3 bucket that I'm going to populate into this table. So again, this is a simple demo, but you can imagine having many hundreds of files in your S3 bucket that you are going to load from S3 into MemSQL. So now that we have the pipeline created, we're going to run start pipeline. And that will effectively start the connection from S3. And one way we can visualize or see the load as it happens is a information schema table. So if I run select star from information schema dot pipelines batches, we'll see that there are batches in progress. And the way that S3 pipelines works is we'll make one batch per file. So in this case, we have 3 batches. There were 3 files in my bucket. We'll see they already have succeeded, and we'll see the rows that they had parsed out as part of that upload. So now if we did a count star from our table, we'll see we now have about 40 million records in our primary fact table. And so that's what we wanted from our load. So now I'm going to do stop pipeline. Great. So that was data loading with pipelines. The pipelines feature in MemSQL is continuously being improved and extended. We're excited to have additional functionality such as loading data from HDFS, as well as a new feature, which is pipelines into stored procedures, which will be a part of the next release. And so there are many ways to ingest data into our database, and we're always working to add more features and connections to these services. So right now I demoed the S3 pipelines, but of course you can load from Kafka as well in this fashion. So now we're going to get to the next big topic, which is probably most relevant to what the exercise we'll be doing is in terms of query tuning, and that is a full understanding of MemSQL as a distributed system. And so most of the webinar attendees would probably know that already that MemSQL consists of aggregator and leaf nodes. MemSQL is a distributed system where you install the same binary on all of the hosts, and you specify the role of each of these hosts in the cluster. One of the aggregators is called the master aggregator, and it maintains the state of the database and connections to all the other hosts in the cluster. And the leaf nodes are the nodes that process your data. And database clients, or the applications that you create, they will connect to one of the aggregator machines. So it's possible to even round robin the connections if you wanted to a different aggregator for each client that's open. Many of our customers use the MySQL protocol or MySQL connection using their application or through a standard dashboard tool to connect to one of the aggregator machines. And so it's worth noting that MemSQL follows the MySQL wire protocol. We are compatible with ODBC or JDBC drivers that you would find for MySQL. The syntax is largely the same, and the functionality and connection will work the same way as it would for a MySQL system, which is, again, the standard that we follow. The leaf nodes in the cluster are the ones that are partitioned, and they actually store and process the data for our queries. So once we start running this query, we'll see the effect on the partitions, and we'll see at that level how the data is distributed. And so the next slide here is meant to give a full picture on choosing a shard key in MemSQL and how we differentiate that from other concepts that we've already talked about. So in a schema for MemSQL, every distributed table that you create will have one shard key. And this is necessary for MemSQL because depending on how many leaf nodes you have, we have to divide the data amongst the nodes for optimal storage and data processing. It's okay to have a non-unique shard key. For example, you can have a concatenation of 3 different or more different fields in your shard key. So this slide gives an example where the ID, a click ID, and a user ID are all concatenated together. In practice, all that it does is it runs a hash function on the concatenation of these values for each row. And so the main purpose of the shard key is just to determine the partition to which every row is going to belong. If you don't end up specifying a shard key, we're going to use the primary key. And if you don't have a primary key in the table, MemSQL will default to having an empty shard key, which means the data is randomly partitioned amongst the nodes, which is completely fine in some use cases. Again, types of queries and the data volumes that you're expecting as to the shard key that is necessary for the table. There are definitely considerations to be made in designing your system and your schemas, not only from a row store versus column store perspective, but also for how you choose your shard key, because that's going to ultimately affect the workload itself. So we're going to talk in the next slide about single partition versus fan out queries. And so the notion there is that if you have a query that has equality for all of your shard key columns, you get the benefits of only having to query one specific place. So again, when you insert data to an aggregator, it will choose one of these partitions on the leaf node hosts to insert the data to. And so if you're looking for a piece of data based on that same shard key, it will know where that data is stored.
Hey, Alec, before we go on to the, thanks. Before we go on to the discussion of sort of different types of queries with respect to how sharding works, can you comment a little bit on how shard keys, what they mean relative to, earlier on you were talking about column store, you mentioned the column store sort key, and I myself have sometimes been kind of confused about that, and I've seen other people get confused about it too, because it seems like they're both kind of telling you similar information, right? They're both telling you something like how the data is organized in the cluster. So
right.
how does the shard key and the sort key, how do they differ from one another conceptually and sort of in practice when it comes to designing a schema correctly?
Right. Distinction between the two. So the shard key is a property of every MemSQL table, regardless of whether it's a row store or a column store table. And so as we talked about in this diagram, the shard key will take the input of a given row and decide where in the distributed system to put it. And for the row store or column store sort key, the point of sorting the data is to get maximum performance from your disks when you're querying the cluster. So there are decisions to make in your application, in your schema design, for both the shard key and how you want to fan out or distribute the data, if at all, and also how you want to sort the data if it's going to live on disk. So in memory, we have the ability to add indexes and use primary keys in row store, and that would act as a MySQL functionality would. In the column store, the sort key is an extra piece that we need to have to optimize the query performance, because even though you can have data all in one partition, it might not be sorted correctly. And so the sort key is meant to delineate specifically within each host and within each partition how the data is sorted optimally for the use case. And so I'll go back quickly to our example here, remembering our schemas. So if I quickly do show tables and the show create table fact supply order, we'll see that we have this sort key and we have a shard key that right now is empty. And this was added by default by MemSQL when we created the table. So in fact, what we can do is recreate the table if we wanted to, if we had queries that would take advantage of the single partition parallelism. And that's what I'm going to talk about in the next slide. So the difference in the query optimizer for MemSQL between single partition and fan out queries depends on what your shard key is. So this is irrespective of the storage model. And right now we're talking about the distributed nature of the queries in MemSQL. So when you match on the shard key specifically, if you had a shard key and you're looking for a row or a set of rows that match your shard key, which may be a unique identifier, what can happen is when you match on that key, it will know that it only has to go to one specific partition in the database. And thus it would only look for one single row or set of rows that pertain to that shard key. In contrast, any other query you run against MemSQL will take advantage of the full hardware and parallelism of the cluster, because it will allow you to process all the data evenly amongst the partitions. And so most analytical queries will use this fashion. And so the sharding mechanism is not the type of queries that you would be running.
Hey, Alec?
Yeah, Jeremy, did you have a question?
Yeah, I did have one more on this slide, if that's okay. What are the implications? Are the implications of this kind of what you would expect them to be as far as hardware selection goes, right? So this kind of makes it look like if you have a lot of fan-out queries, then the sort of potential weakest link is going to be AG2 in that diagram that you have there. So the first place you should be looking when you're performance tuning and sort of refining the cluster architecture is around making sure the aggregators are not lacking, are not sort of resource starved. Whereas for the single partition queries, it looks like the single partition query is only going to be as fast as leaf 4. So that would sort of point you in a different direction as far as optimizing and refining around hardware selection. Is that accurate, or is there more that you would say about that?
Yeah, definitely. So in terms of maximizing, the hardware selection, one thing that's important to note, especially for these transactional use cases, is that it allows you to get better performance on many queries coming in at the same time. And so, for example, if you had a sharding mechanism based on a user ID or a product ID, what we can do is shard based on that data, and in very high volumes of querying and updating, you can maintain that transactionality for all of the queries that happen. So you can look at used, but in practice, with a lot of use cases where single partitions become relevant, is when you have a high volume of queries that are going to be looking across all partitions. Because again, the distributed nature depends on the hash function from within the system. And so it's only internal to MemSQL which partition each piece of data is going to live. And so in those use cases, it makes sense to really take advantage of the sharding mechanism. So in this specific example, our table, the query that we're optimizing for is more analytic in nature, and it will have to look across all the partitions anyway. So it is not as necessary to have an explicit shard key created, although we could do one for this use case as well. So if we had a sharding mechanism, one thing to keep in note, and this pertains to how MemSQL performs on your queries, is the notion of a distributed join. And this is something that's very important when we talk about query tuning. And this next couple of slides give an indication, an example of how that's going to work. So in this simple example, we're joining two tables together. Neither of the tables are sharded, and they're looking for a color attribute to be joined upon. Is that because there are two different leaf nodes in this system, and because the data is not sharded at the moment, what we have to do to actually execute the query is move data around from partition to partition. And this is the semantics of how internally we actually process the queries. When the aggregator or the client receives the query from the user, it has to then parse it into a set of separate queries that will be executed against MemSQL on the leaf nodes directly. And so because there are values with different colors on each of the leaves, and we have to compare where the colors are equal, we have to actually look at the values when these colors are on the same hosts, which means we have to reshuffle some of the data around. And so this distributed join problem is not unique to MemSQL. It happens in most distributed systems as well. And so it's a common thing to look out for in our queries and our schema designs so that we can make sure we optimize the queries themselves. So to get a little more specific on what a distributed join is, it's a query that does not match or filter on the shard key in MemSQL, and it will cause network overhead because we have to move data physically around from one host to the other, or to the rest of the leaf nodes in most cases. There are two ways that a distributed join can happen. The first is a reshuffle operation, and then there's also a broadcast operation. And the MemSQL optimizer will choose methods running the query. So the reshuffle operation will actually reshard the data of the smaller table in the join, or in this case depicted by this image, the result table of a subquery, and it will do that so it can match the result of the large table. With a broadcast operation, it's even simpler than that, because what happens is we'll send the entire small table or side of the join to the rest of the other nodes to actually complete the query. And so when we're looking at query plans in MemSQL, which is what we are about to do, we will notice these two operators and have to look out for them so that we can optimize the performance and minimize any network impact that would happen as part of the queries. So before we talk about eliminating the distributed join, what we're going to do is try running our query, our sample query on our data set. And so if I go over here to my query, I'll select this query and I'll run it against our data set. And we'll see the results come back. We have 5 addresses. It came back fairly quickly in terms of the plan being executed. But what we can do is now look at the individual operators within the query. So one tactic you can do this in MemSQL is the explain plan. So when you're looking for the granular information about the MemSQL optimizer, it helps to run explain before your query, and this will tell you how the query is going to be executed. And the way to read an explain plan is to first look at the bottom of the explain plan, because this shows the operator that's going to happen first, and then you scroll to the top to see the results of the query. The first operator we're doing as part of this analytic query against our data set is a column store scan against our fact table. So it's using the sort key to look through and scan all of the facts in the table. And then we're doing a couple of operations. This case, there are Bloom filters that are optimized for looking specifically at both the product ID and supplier ID, because we need. We'll see a broadcast operator up here, which is distributing and broadcasting the smaller table, which in this case is dim product, which has only 1,000 records in our case. After it's been filtered for all the records that are looking for aspirin as the product type, it's going to be broadcast to the rest of the cluster to perform what we then do is a hash join after that to maintain all the records that have that product ID. We can keep looking above here, but I won't spend too much time looking at the details of the plan. But we do notice that before some of the other joins, because we have to join to all of our dimensions in this query, we'll see a repartition that has to happen, because we're also looking at the supplier table dimension as well as the time dimension, which is then filtered by anything pertaining to 2016. So again, just to visualize and look at the query itself, again, we have the query that's looking to join across all of the dimensions in our data set. So let me just run the query again. So again, if we look at the query itself, it's doing 3 joins to the dimensions, and that is that. Because if we notice, the dimensions themselves, the way that they were created is they have a primary key and thus are sharded on something differently than the fact table, which is not sharded. And that is what's causing the overhead of these repartition operations. So show create table dim time, for example, would show us that there's a primary key on the time ID field. And so anytime we're doing a match to the fact table based on the time ID, the dimensions are going to have to be broadcast to the rest of the nodes, because we can't complete the join without matching against each of the leaf nodes, since they're not sharded the same way. So to explain this in a little bit more in depth, so that it makes sense for all the attendees, is what we can try and do is match on the shard key to perform what we call a local join. The local join, if we ensures that there's no network overhead to the join being performed, and that's because each partition has the same data for that given shard key value. So we can ensure that you don't have to match any other records to each other to perform the join. Now, there's one other way that we're going to use in this use case to actually force a local join on each of the operators, and that's the notion of reference tables. So reference tables in MemSQL are tables that we actually replicate to each of the leaf nodes directly. They are most useful when you have small dimensions, memory in most use cases, and less frequently updated because for these dimension tables, they're going to be replicated across to all of the leaf nodes. So what I'm going to do is we're actually going to change our schema here, and we're going to choose to make our dimensions all reference tables, and we're going to see the results of the query to see if it actually performs better and we can change the plan. So quickly what I'll do is go back to our schema. And bear with me while I find my mouse. It doesn't seem to be here. And we'll see this new syntax for create reference table, which I'm going to then create on the cluster. So the reference table, the only thing we changed was the word reference in front of the create table. It's going to recreate all of our dimensions with the substring ref at the end, and it will still preserve the same primary key. So we have the same tables here. Now I'm going to simply insert the data from the old reference tables to the new one by doing a insert, which is here. So if we do a show tables at this point, we'll see our old dimension tables and our new dimension. We're going to now visualize the query itself by looking at the reference tables. So this query that I'm about to show you is the same exact query we ran before, but on the reference tables, dim time ref, dim supplier ref, dim product ref, instead of the former dimension tables that we had. And so if we first want to run and visualize that explain plan, what we'll see immediately is that there are no broadcast or repartition operations in the explain plan, which means that there's no data reshuffling or no overhead of moving the data around. So we've effectively eliminated all the distributed joins. Now, if I run the query, we'll see that it comes back in about the same time. And once we cache the query plan in MemSQL, it'll return the same results because we've moved the data to the new reference tables. We can imagine as this database scales out and as you add more data to the fact table, the dimension tables become more important as reference tables because they will eliminate the need to move around data during your distributed join. So that is how we optimize for our use case and our query by creating reference tables. Again, we talked about matching the shard keys, and that will also create a local join. In our case, what we did is we created reference tables. So now a quick aside about query tuning and how to look for these operations, which prints the MemSQL optimizer's planned execution for the query. So you'll see things like table scan, hash join, repartition, which we've all seen in our query plan. What we can also do is profile, and that runs the query profiling tool, which gives more granular information about each execution step in MemSQL. And so if we run profile before our query and then the term show profile, profile will execute the query as if it was normal, and it will save the steps for execution in the profiler so that when we run the command show profile, it outputs the same query plan, but it has more statistics about how long it took for each partition, the execution time for each step. So in this column store scan, it took 45 milliseconds. It shows the start time for each of these operations noted by a partition. So the first partition started at 0.535, and the last partition started at 0.552, and that's to note the differences in execution based on the partitions in the database. And then we'll see for all the other operators, they have the same type of information. They keep track of the actual rows that were executed on, the execution time for each of the operations, and then the start time. And so this is how we can look at performance in granular detail and see where any bottlenecks might be in terms of network traffic overhead, and based on the query profile, which operations are taking the longest. And so this is the query we've been optimizing. We've effectively eliminated the distributed joins by creating reference tables. The two other commands I'd like to talk about before we get to the last section in this webinar are analyze and optimize. So these are two other MemSQL specific commands that are not going to profile specific queries, but they're also to maximize performance. So analyze table, which you might be familiar with, is a way to calculate your table statistics, your cardinality estimations, so we can help the MemSQL optimizer choose the best query plan. And we recommend to do this after any significant increase or a refresh of your data set. So for example, my load from S3, it probably would help to run the analyze table to make sure that those statistics are up to date. The other command is optimize table, and this can be run as optimize table full or optimize table flush. The optimize table full will sort the data based on your primary key, whether it's in the row store based on an index scan, or whether it's in the column store sorted on your column store sort key. The second command, the optimize table flush, is a column store only command that actually flushes the entire in-memory segment down to disk. And again, we recommend doing this one after any large batch loads to column store, as it will effectively sort your data and move it to disk. And that's, again, part of a column store functionality. So I want to quickly cover the last section before we answer a couple of questions in the webinar. And the last section pertains to operationalizing MemSQL. So we've already talked about how data and your schemas. Now we can look at monitoring and workload management. And these are key pieces in the MemSQL deployment. The first two commands, really first command to be aware of is the command show status extended. And we can run this against my cluster right now. The output of show status extended is very verbose, and it's meant to give a granular picture of each of the memory allocations as well as other information relevant to MemSQL. So we'll see the home directories for all the logs in here. We'll see the number of threads that are actively running against our database, the number of connections as well. And what we can also see are the allocators specifically for MemSQL. So a couple to keep an eye on would be the total server memory parameter, which shows how much memory MemSQL is using for that entire machine. So total server memory is the summation of all the other allocators that you see here. We have a docs page related to this show status command that will allow you to track and monitor certain values within show status. And most of our customers are implementing monitoring mechanisms to look at this information on a hourly or even minute basis. The other command quickly that we can run is this memory query that looks at the memory usage. And this is something I can share after our session. This is meant to look at the memory usage per table in our database, and will give us that information. The other thing I want to touch on is the management views capability within MemSQL. And this is a relatively new feature that we've developed that actually gives you very granular information and resource usage about what's happening in your MemSQL cluster. So the activities themselves are categorized into query activities, database activities, and system activities. They are self-explanatory, hopefully, as to the operations in MemSQL. And it requires setting one variable, read advanced counters. And with management views, the tables themselves are a profile of exactly what is happening on the cluster, whether it's the activities that are recently running and using resources, the nodes themselves, and how the status is, or disk usage or network overhead for certain nodes, as well as the queries and activities that are related to the cluster. And so I'm going to demonstrate a couple of queries against our demo cluster. The metrics that are populated in each of these tables are very granular. They range from CPU time to CPU wait time, all the way to your network information. And this is very good at identifying, in cases where you can't identify a bottleneck in a query, you can see what is running against the cluster and what might be using the resources necessary. Answer questions like, what is the most frequent activity type on each node? With this query that looks at the MV activities extended, and joins to look at the nodes themselves. The query that I'm going to run is this partition query. So there's not activity on the cluster right now, but we can run this query itself by just inputting it into the information schema. So if I run use information schema and then look at our partitions, we'll see, again, it gives an output based on the number of partitions and the active activity on the database. So if you have a memory-intensive query running against the database, it's a good idea to run something like this that would give you the tracking of memory information based on that. I apologize for the noise in the background of our room here. So we can answer many questions using MV activities. I will share this slide deck with the attendees after our session. I wanted to answer a couple of questions that have come up on the webinar and then wrap up the presentation today. So thank you for attending. And one question that we had from one of the viewers was about the sort key order. Is there a meaning to having the order for the sort key if the columns are kept separately? The answer is yes. The sort key order is meant to helpful for each column. And the way that you can think about it is in filtering queries, you might want to filter by time and then by another attribute like product ID. So it helps to first, as the first element of the sort key, put the element that is going to be filtered the most, such as time. If every one of your queries is looking across a specific set of weeks, and then you can from there, once it was within that certain bucket of time, once it's organized and sorted by day, it would then be sorted by product ID. So it helps to identify the filters in the queries themselves before choosing the sort key and column store so that you can optimize the performance for both. Another question we had is about the flushing of column store tables. If there's still some memory consumed by the table, is this a cache? And the answer is that relates to the garbage collection mechanism in MemSQL. So when we actually flush rows from the column store memory to disk, in the in-memory tables, it actually uses a bit of memory to mark those rows as deleted. And in future background executions, the garbage collection mechanism will free that memory back to you. So it's likely in that use case, if there's less resource usage on the cluster, so it might not pick up the memory, but the memory usage is there just to mark the rows as deleted, and it will eventually be freed back to MemSQL and the system. And so with that, I want to wrap up the webcast and make 2 more announcements about our future activities from MemSQL. So if you have any questions, I'd recommend that you sign up for our tech office hours. I'm going to be hosting a set of office hours next week on the 31st of January. This will be a great resource to ask personalized questions related to schema design or sharding or any of the topics that we talked about today. We can go through a more granular view of the use case, and I'm happy to cover more topics in depth about MemSQL. And we're going to be continuing these office hours. If you can't make it on January 31st, we'll have another iteration next month for anyone to be able to join. And the next announcement and the final announcement is for our training program. If you liked any of the information today in our webcast and you'd like to learn more and be practicing in a hands-on environment, we have a MemSQL training program that's being offered next week from the 30th to the 1st. And we have a special discount for the participants in today's webcast where you'll save 50% if you're one of the first 5 people to register. And so the code is here, and we'll send it out after the webcast is over. And that's if you wanted to get more operational hands-on experience like we did today with our example, but actually trying it in your own environment. So I'd highly recommend looking at our training programs. It's very helpful to get started with MemSQL. So it was very helpful to be able to present all the topics with you, and I hope that we can continually provide these webcasts so that all our customers and users will be able to know the latest about MemSQL. And I look forward to chatting with some of you in our office hours next week for any more questions or further feedback. Thank you all for attending. Have a great rest of your day.